Hello and welcome. Today's webinar is collecting and analyzing pedestrian behaviors at intersections using LiDAR tracking technologies. My name is Lacey Friedley. I am the Communications Coordinator at Portland State University's Transportation Research and Education Center. PEC leads the National Institute for Transportation and Communities, a university transportation center funded by the U.S. Department of Transportation. NITC consortium members, in addition to PSU, are the University of Utah, University of Oregon, University of Arizona, University of Texas at Arlington, and the Oregon Institute of Technology. NITC's research priority is improving mobility of people and goods to build strong communities. Our presenters today are Dr. Taylor Lee of the University of Texas at Arlington and Dr. Sirisha Kothuri of Portland State University. Dr. Lee is an assistant professor of transportation engineering at UTA. He has over 20 years of experience as a professor, traffic engineer, ITS engineer, and project manager at various companies and research institutes. His research and professional practices focus on intelligent transportation systems, smart sensor development, AI, and big data analytics. Dr. Kothuri is a senior research associate in the Department of Civil and Environmental Engineering at Portland State University. Dr. Kothuri's primary research interests are in the areas of multimodal traffic operations, bicycle and pedestrian counting, and safety. She is the research co-chair of the Transportation Research Board's Pedestrians Committee and the Bicycle and Pedestrian Data Subcommittee, and a member of the Traffic Signal Systems Committee. Before diving into the presentation, I'd like to let you know about another upcoming NITC webinar. On June 8th, Rebecca Malden, Stephen Mattingly, and Rupal Parekh of UT Arlington will share research on transportation resources and behaviors among older immigrants and migrants. Today's presentation will be about 40 minutes long, then we'll have 15 minutes to answer your questions. During the presentation, please submit your questions via the Zoom Q&A. After the webinar, you will receive an email with a link to the video recording and presentation slides. If you are tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. A certificate of completion will be posted on the event page within 24 hours after the webinar ends. And with that, I will turn it over to our presenters.
Is my screen okay? Can you see my screen?
Yes.
Is that okay? Sirisha, can you see my screen?
Yes, I can see it.
Okay. Okay. Thanks, Becca. Good afternoon, everyone, or good morning, everyone. My name is Taylor Lee. Today, I'm gonna work together with Sirisha to present our project. This is our first project on LiDAR to collect pedestrian behaviors at intersections using advanced LiDAR sensing technologies. So here's the outline for today's presentation. First, I will give an introduction on the background or motivation for our research and the motivations. Then Sirisha will take over, then give a later review and technology reviews to see what's the gap of current technology and compare with the LiDAR sensors. Then I will take over the mic again, give the introduction of our LiDAR solutions. And also we're gonna give a field test study. We deployed at 2 intersections and collected pedestrian behaviors, then try to figure out what it can offer. And also I will offer a demo system. A demo system is used for us developing our system. This which was a live system in the city of Irvine. I feel very appreciative of their help. And also introduce some future work. In fact, since the project is finished one year ago, so it's just current work. So first is introductions and motivation. So myself has been working on traffic signal for many years. So almost most of the time, like many other colleagues, we focus on how to reduce congestions, how to improve the mobilities. Then one day I read a report, National Highway Safety Administration reported the pedestrian fatality keep increased by 44% in 10 years and reached the highest in 30 years. That was a stunning fact. In fact, I just asked myself and a few close friends. So we have been working on traffic signal for many years. Then if we were a student, we're gonna get an F. So because safety will be the first, because the creation of intersection or signalized intersection is to increase safety. Now we are not really increasing safety. And also the safety issue result a lot of not only the huge social economic losses, also is a shattered family and broken hearts. It also means we are missing some transportation equities because as according to the newest FHWA Associate Administration for Safety, transportation equity means safety for everyone. So I think this statement also reflects a few emerging funding opportunities like SS4A and another one, Intersection Safety Challenge Award, things like that. Okay, so that's that because our efforts, ideas, came to these ideas a few years before all those funding opportunities. So it has been working on the things 2020, and the NITC provide us with the first funding. Then after that, we have another related project as well. So to provide pedestrian safety, so we first lay out what we need to do, what we are missing. First question we're facing when we're reading the literature is we do not have a lot of literature on pedestrian behavior at intersection. In fact, as a professor, when I taught traffic engineering, I even cited some literature on 1984, even in 2023. There's some study in the textbook. And then, and also the latest pedestrian behavior at intersections is 20 years ago. So we're missing a lot of data analysis literature on this. But to have these studies, we must collect a lot of data, especially after we have almost new generations, or after emerging smartphones, all the walking behavior changed. So we no longer look straight. We all keep looking at the small screens. When we walk, we are likely distracted. We are maybe walk slower than before. They are all those new technology all affecting our behavior, but those behavior have not been addressed by any guidelines. So this creates a lot of issues. So then after we collect data, or we think the next step, we have to revisit all the guidelines, pedestrian facility design, like in Green Book or heavy engineering, etc., to see those guidelines are still suitable for the latest pedestrian behavior study to protect pedestrians. The third is once we have the facility design update, then we need to think about the signal system itself. Signal system is by nature, the current signal system that's for vehicles. So they have a minimal consideration for pedestrians. In fact, in today, after we give so many permissive movement allowed at intersections, we could have a near miss at any second during the yellow, during the red, during the red, or even during the yellow green. So that's something we need to address. Then, of course, after all of this, we have to go beyond the traffic signal itself. We need to go through how to integrate with other systems like a street system, lighting system, or even the connect automated vehicle infrastructure. So all things together, we should have a pedestrian safety improvement. But of course, for today, we cannot cover all of them. So we're gonna cover most of the first two parts, especially the first part, pedestrian behavior study. Like a journey of 1,000 miles always begin with a single step. So we are trying to provide our first research fundings during this project. So I'm gonna give the mic to Sirisha to introduce some literature on technical reviews on pedestrian and behaviors. Go ahead, please.
Thanks, Taylor. So before starting the actual study, we wanted to review the literature and also perform a quick scan of the existing technologies to see what is out there. So one of the important performance metrics at signalized intersections is the perception reaction time, which basically refers to the time between when the pedestrian first receives the walk indication to the time when they actually start the walk. This value is really important for human factors research, for signal timing and crash reconstruction studies. The average PR time that has been used in the literature is 1 second. However, as Taylor mentioned before, this value is probably out of date because this is based on data that was collected many, many years ago. And so there is a need to collect more recent data. So one study that was performed over 20 years ago at 6 intersections in Los Angeles found that while most pedestrians started walking within 1 second of the walk indication, these values were lower when pedestrians were anticipating a light change and higher when they were distracted. And given the incidence and the proliferation of smartphones today, we need to have collect more data and basically update these values.
Next slide.
Yeah, thanks. Another important performance measure that we want to collect and look at is delay. And delay is basically used to quantify the operational level of service of intersections and is used for intersection mobility. So on the vehicular front, you have many studies and many methods to estimate vehicular delay, and the signal timing objectives are to reduce delay for vehicles at intersections. But pedestrian delay has not yet been given much attention. Over the last few years, there have been some studies trying to estimate pedestrian delay and measure pedestrian delay with the recent ATSPM's automated traffic signal performance measures. Past research has shown that pedestrians become really impatient when delays exceed 30 seconds or between 30 to 50 seconds. And this has an implication for safety because pedestrians can start crossing against the signal. So the compliance is violated and that can have an implication on safety. Alternately, when pedestrian delays are low, so when delays are less than 10 seconds, then compliance is high. Pedestrian delay is, as I mentioned, is available as part of the high resolution data and the ATSPMs, but many agencies are still not routinely collecting it or using it in practice. We also wanted to look at pedestrian detection at intersections, and since the 1930s, pedestrian detection has been accomplished through the use of pedestrian push buttons. So the design has not changed much until the development of the APS or accessible pedestrian signals. These offer auditory messages and tactile feedback to pedestrians with impairments. So research has shown that a lot of the pedestrians do not really use the push button, but installing these push buttons with the APS increased the proportion of pedestrians who pressed the button and waited for the walk indication. So the APS is definitely helping helping pedestrians to cross the street safely. So there is a growing recognition, however, that this pedestrian detection needs to be passive, similar to what has been used for vehicles. So when vehicles approach the signalized intersections, they don't have to do anything and they're automatically detected. However, we expect the pedestrians to press the push button and perform that additional action. But passive detection is something that that can really help increase the efficiency in the system. There are a number of sensors that are being tested currently. Infrared and microwave sensors have been tested in the past, but they're generally not used a lot at signalized intersections. In the UK, puff-in crossings have been tested, and those crossings allow the walk indication to be extended dynamically, especially if older pedestrians or slower pedestrians have not finished their crossing, but those have also been not widely used. Recent advances in technology have led to these new sensors for detection. So you have LiDAR sensors, video sensors, and radar sensors. Thermal and infrared are also available. Video sensors have been used at intersections, but they suffer from the fact that environmental conditions can affect their performance. So their performance degrades when it is rainy or dark, there's less ambient light or fog, etc. Radar sensors are not really suitable for pedestrian tracking, but LiDAR sensors have shown promise for monitoring and tracking pedestrians in most conditions. And I'll hand it back to Taylor to talk about these LiDAR sensors.
Yes, thanks, Sirisha. So I will continue to explain our solutions using LiDAR to track pedestrians. First thing first, what is LiDAR? Why LiDAR? So LiDAR is a kind of a emerging sensor. It's a method to measuring distance by illuminating the target with a laser light, measuring the time of reflection light, taking to return to the sensor. I'm just reading the cat raising you. Two types in terms, one is, we have two types. One is mechanical. They have a different name. Sometimes they call the 360-degree LiDAR. Sometimes called mechanical. Sometimes they call the spinner. They're just using one LiDAR to cover 360 degrees. Because there's a micro mirror in it. So we have a transmitter, then send out the LiDAR beams, maybe multiple lines together. So using one fast spinning mirror, so they can cover all the locations. So whenever a receive it is blocked by some objects, it cannot go through. They can return and received by the receivers as well. So we have quite a few product in the market. In fact, here we probably need to update it because LiDAR market is still very dynamic. Companies come and go, and but eventually we're gonna have a few strongest survive. And one physical feature for LiDAR beams is it cannot penetrate mental frame of human bodies. Just like if you use a laser beam to, as a presenter, you point on to the blackboard, they can show a dot. So pretty much the very similar idea. So if you go to a music concert, they're gonna see many laser beams together. So you're probably gonna see something like that. But one thing I can tell you is the LiDAR sensors laser is safe to eyes. So will not, it's called class 1, will not hurt your eyes. So this is not really visible directly. In fact, this are reconstructed using software in the LiDAR wheels. So in fact, at a certain time, I was asked a question by an agency. They expressed the concern. So what if your LiDAR make our crew blind? So I said, no, I couldn't. In fact, to be safe, in the very beginning, I also bought a few goggles for me and my students wear it. But over time, after having more knowledge of a LiDAR, I don't think it's necessary. We just throw it away. Okay, so then using LiDAR, how to give the shape of objects. So it's kind of like something like that. So you must know this very famous movie if you have a kids. So it's kind of like you have a multiple lasers just randomly shooting two objects. And if they can do not shoot them, they're gonna pass them. But if you shoot this guy, they're gonna return to receive by the receiver. So by measuring the dimension of a received returned points, you can pretty much get the shape and height dimension for the objects. Using that objects, then you can further classify as the human, bike, and vehicles or trucks, etc. So regarding the LiDAR sensors, we have a 3-level of algorithm or 3-level of concerns. The first one is hardware algorithm. In fact, that's a concern for LiDAR manufacturers. So LiDAR, among all the LiDAR hardwares, every LiDAR sensor or manufacturer, they build things differently and also distinguish from each other for niche market. So that algorithm in hardware is more like how to make a LiDAR sensor more efficient, maybe energy efficient, reliable, can last longer time during the hot weather, so they can generate useful raw points. It's a concern of a LiDAR sensor manufacturer. Those raw data is not actionable to users. It's kind of like you see the figure, LiDAR can automatically return a lot of objects, give you the shape. Given the intensity of the LiDAR point clouds, using your human eyes, you can clearly see this is the house, this is the tree, etc. But those points doesn't make any different sense to a computer unless we apply a perception software on top of the raw data. So then we go into the next level of algorithm. We call it perception and classification. So this software has been using for automated vehicle for a long time. So when vehicles are moving forward, they have a spinner or a solid state LiDAR, so they can get some points. So if the LiDAR scan object will reflect more points than the other empty location. So then they can be classed as objects. Then the object can further into classifications. So those part for traffic applications, we have to have the perception software. So when I started, there's not many options. So there's options, but they're very expensive. So in the end, I choose one LiDAR sensor with some OEM perception software which I can afford. So ever since has been using that sensor ever since then. I try not to mention the name, but if you're interested, you can send me an email. I can tell you the name. Okay. So the third part is we call the integration algorithm. That's really my efforts. Where my efforts is really for domain-specific applications. For instance, in our case, we integrate a LiDAR tracking algorithm. This is off the shelf with a real-time traffic signal status collected from the intersection. Okay, so based on those information and some background knowledge, we create multiple applications, and pedestrian behavior collection is one of them. So here's some new trend for LiDAR sensors based on our years of observations, because we are just observers for this market. So we are researchers, we neither build sensors nor sell sensors. We just try to observe. Hopefully, eventually we have multiple options. Eventually, LiDAR sensor could be like as rich as cameras, but unfortunately not yet. So in fact, LiDAR manufacturers are facing a lot of challenge in late 2022 and 2023 so far. I guess you must be aware of that if you closely watch the stock market. And the whole market is more diverse. So a few years ago, all of LiDAR manufacturers, they're focused on autonomous vehicles. They're trying to have a volume sales or production for autonomous vehicles. But since last year, the target market have become more and more diverse. In fact, some LiDAR sensor has a more high priority on infrastructure, intelligent intersection infrastructure. Some LiDAR sensors sells millions of dollars of product to toll road to measure vehicles. And also for the perception software, there's a lot of OEM perception software. I mean, you buy LiDAR from company A, you can buy a perception software from company B. You can put them together. But also the LiDAR and more LiDAR hardware manufacturers, they can provide their own OEM perception software more and more. So we have more and more options. So what is the LiDAR advantage over the others? As still a relatively more expensive than the current traffic sensors, why we want to choose the LiDAR? So first, LiDAR has three, I think, outstanding benefit. First is LiDAR is prominent performance in tracking in dark conditions. I got this tease video for 2 years Halloween that's recorded by a LiDAR company. So this guy using a video, in fact, that 2 person walking behind, we cannot see on the screen. But if you use a LiDAR sensor to get them, you can see 2 person are walking beside. That's really his friend pretend to be ghost. But until the end, you can see some this appear in the middle. So let's give you a illustration how the LiDAR outperforms in the dark condition compared to videos. The second is the raw data has a very high fidelity. So this is 2 comparison between LiDAR raw data and highest resolution radar data. So you can see using our human eyes, we can see this is a bridge, this is a human, this is a vehicle, etc. But using the best LiDAR radar sensors, we can only see there's an object, but we cannot tell what it is. This to me is more like a refrigerator rather than human. So the point is, if we cannot recognize a person, something using our eyes, it's gonna be very difficult for any algorithm, AI or deep learning to recognize them for us. Although it's, I used to say impossible, but now I think now I need to be open. So it's very difficult to do that. But LiDAR provide a high ceiling. That means make our algorithm work, recognize people much easier. And another advantage for LiDAR sensing is it's measure 3 dimension. It's not only the length or width and also height. They can create a lot of new applications in traffic management. For instance, at certain ramps, they may want to measure the vehicle's height. Okay, using the height. So if the vehicle too high, they may try to stop the vehicle before it hitting the a low bridge downstream. This is one example. But using height to measure traffic, we can have many interesting applications. Although we haven't started anything yet, but this just pave the road for those applications. So now come to the solutions, what we have. First is we bought 4 LiDAR sensors. The LiDAR sensor we bought is sometimes called solid state, some called somebody called this flash, but I would rather call it directional because it behaves pretty much like a camera. It has a fixed field of view. So in other words, in order to cover 1 intersections, you're probably gonna need 4 LiDAR sensors. And they facing into intersection and have some overlap. Using perception software, 1 pedestrian can be tracked from 1 sensor and taken over by the other sensor without losing the ID. The temporary ID keep is the same person. So this is really just a commercial available solution. But our solutions on top of this edge computers, which also from the vendor. So we build our own algorithm. Algorithm first is we using NTCIP protocol to retrieve the real-time synchronous traffic signal state, the current green, current yellow detector states, etc. Then put some like a filter with a LiDAR tracking information and send the information back and create a scenario and send the raw data back, upload to our central machine. So we already have. It's not for this project, it's for more general purposes. We already built a light ATS-MPM system. We call the UT in motion. So on top of the Purdue coordination diagram, so we have add more pedestrian information on it. Okay, this is our system solutions. So now we come to the case study and the findings. Before I give to Sirisha again, I will try to explain first what we are tracking. So Sirisha has explained we identified a few key behaviors data we want to collect. The first is pedestrians waiting time. The second via pedestrians perceptual reaction time to the walk indication. The third is pedestrian walking distance. So instead of using second vehicle trajectories, we decide to use zone-based because that really reflect how the highway design guidelines like a green book they work. In fact, we more care about the average speed or we care about the average perception reactions, but we don't really care if the pedestrian walking in the middle get faster, then slow down, then come to the average speed. So that part, we don't really care. We care about from here to here. Having said that, we just use the zone to track the vehicles. It gives the event-based, whenever a pedestrian reach a zone, we can mark a time event. Something we draw at each corner, we draw a pedestrian waiting zone. Whenever a pedestrian walking into that zone, so the pedestrian is considered potentially relevant to the intersection. If the pedestrian stop and has developed time in the waiting zone for a certain threshold, we consider it's waiting for crossing either this way or that way. But of course, if the pedestrian come and go, then this pedestrian just passing. It's not relevant. We are not track them. So then in the meanwhile, the program will we're collecting the real-time traffic signal status. So whenever the walk sign is on, which can be retrieved from the signal controllers, then we will track we're gonna see this pedestrian will keep walking. We have an entering zone and leaving zone. Whenever pedestrian from waiting zone entering zone, that means the vehicles enter intersection, start entering intersection. So the time from the vehicle start move to the entering time is, in fact, that's a walk time we use for to determine the walk time differences. Please note that the perception reaction time here we are measuring is not really the perception reaction time in general. Because when we talk about perception reception time in general, we more like whenever the pedestrian knows the walk sign is on, he began to move. That is a general perception reaction time we're using for teaching or for traffic engineering analysis. But in our case, we call it effective perception reaction time. That time including both the general perception reaction, also the time it walked from where it stand to where they enter intersection. That time also need to consider because that time determines the walk time design. Okay, then once the pedestrian reaches the other side, then we measure because we have a different time steps. Whenever a pedestrian enter, we have a time step. Whenever a vehicle enter the cross zone during the walk, we have a time step 2. Then whenever the pedestrian reaches the other side, this ending zone, then we have another the third time step. Using those time steps, we kind of doing that. Okay. Now I give turn over to Sirisha to introduce our case studies.
Yeah. So we selected 2 sites for data collection. The first site was in the city of Arlington, and the intersection that was selected was the intersection of the UTA Boulevard with South Cooper Street. This location was right on the University of Texas at Arlington's campus, so right outside the engineering building. And so it was expected to have high pedestrian volumes, especially when school's in session. There are 4 crosswalks at this intersection, as you can see, and these phase numbers correspond to the parallel vehicle phases, so 2, 4, 6, and 8. The second site we chose was West Walnut Hill Lane with North Beltline Road. This is an intersection in Irving, Texas. It is a location that is very close to the Dallas-Fort Worth International Airport. There are also 4 crosswalks at this intersection. The numbering slightly different with 2, 3, 4, and 6. As Taylor mentioned, 4 LiDAR devices were set up at each of these locations to monitor and observe pedestrians as they were crossing. Next slide, please. So we put these devices up and then started collecting data. And so this is basically a plot of the pedestrian volumes that we were seeing at the UTA Boulevard and South Cooper intersection. So at this location, data was collected between July and December of 2021. And because this is on the campus of UTA, we observed almost 50,250 pedestrians crossing all four crosswalks across the across the 5 months of observation. There were some missing entries of, like in some instances, the entering time or the leaving time. Those sorts of things were sometimes missing if pedestrians disappeared from the entering those waiting zones, as Taylor mentioned. And so all those records were clean. And so we ended up with over 50,000 pedestrian observations that we looked at further. Next slide, please. So this chart shows the volume distribution for Walnut Hill and Beltline Road intersection. This was a lower volume intersection compared to the previous one. Here we observed the intersection over a longer time period, but we did see a lot of data gaps in the data itself, probably because the data there was some issue with the data transmission or it was disconnected. We had about 4,289 observations recorded at this intersection. And then again, as before, we discarded all the incomplete records, which resulted in about 3,524 pedestrian observations that we looked at for determining the metrics. So once we had our clean data, we looked at these metrics that we had discussed earlier. So these the effective perception reaction time, the average crossing time, and pedestrian delay. So at this intersection, we see that the average perception reaction time or the effective perception reaction time is about 2.1 seconds. At this intersection, there are these audible pedestrian signals present at all 4 locations. And so, and you will see shortly on the next slide, so the presence of APS has provided that auditory cue to pedestrians to start their crossing. And so this has led to a lower effective perception reaction time. Compared to this other intersection, the Walnut Hill and not Beltline Road, here we see that this effective perception reaction time was much higher, and this is a location where there were no APS present. So this APS is providing this additional advantage of alerting all pedestrians to the fact that the walk indication has come on. And then we also computed these average crossing times and average pedestrian delays. And so just showing that this these devices can be very useful for generating pedestrian performance measures real time, which could then later be used for other signal timing and other purposes. So in terms of our findings from the case study, we found that the LiDAR solution that we deployed is able to detect and track pedestrians effectively. We were able to measure average delay, average crossing times, and effective perception reaction times for each pedestrians. And so we're able to generate a lot of data in a relatively short amount of time. And then again, the average PRT times were lower at intersections equipped with APS. And with that, I will pass it back to Taylor to talk about future work.
Yeah. So I would say I'd like to give you a demonstration. I think is one picture is better than 1,000 words. One video is better 1,000 pictures. So we have 1 million, things like that. So this is a really a live environment I recorded when we are building the system. Because we first thought about it, so we were trying to build, because a general road path is we build a system, evaluate in-house, maybe using simulation or something like that. Then we deploy in the field, finding bugs, and fix it. And eventually, we're gonna get a more and more stable. Eventually, it can be a permanent solution. So the first challenge we faced is, in fact, we couldn't really do any development regarding pedestrian in the house. The reason is pedestrian behavior compared to vehicles are very random, much more random than vehicles. Because let's say one example, one vehicle are waiting in a stop bar, they pretty much will not move because they just keep staying. Maybe they can move, so squeeze forward a little bit, but that's all. We can pretty much predict what behaviors. But for pedestrians, waiting pedestrians, in fact, we have been observing, I mean, using our eyes after we get a system installed, we just observe pedestrian walking. I mean, they don't know me, we are monitoring them. So see what they do. In fact, it is a very random. Sometimes pedestrians, when they are waiting, they get bored. Sometimes they kind of get closer to the other one. I don't know what they are doing. And sometimes they go behind the pole, then leave the vision of a LiDAR. Sometimes they walk around. Sometimes they go back and forth. In fact, they have all the behaviors we cannot really expect. So we cannot simulate using any simulation to simulate those behaviors in the lab. So as a result, we have to build a system using a lab system. In fact, again, I feel highly appreciated for our local agencies' help, their passion to help us to make it work. So in fact, because we are touching their signal, so we are using their live ATMS system to do the system. So after we get familiar enough, I know what I'm doing, and I have not messed up their system. So they say, okay, I give it to you for a few weeks. So in this video, you can see I have live stream cameras, and we have LiDAR sensors, web view. We can see the real-time traffic. And also from the controllers web interface, see the real-time controllers. This is a console for my software report, the event is. So we just compare this one to here and to here to validate and identify any unusual behaviors we couldn't figure out in the lab. So this process is iterative. We repeat many times. And we iterate our algorithm many times. In fact, sometimes myself observe those data for 100 hours. So trying to understand. So you see one person, in fact, for this video, it's like our researchers. That's this person walking. So you can see whenever they reach here, it's supposed to report something. So we just gave you a demonstration how the system built. So in case in the future, if you're researchers or company, you're trying to build your own LiDAR algorithm, if it's to target our vulnerable road users like bikes, pedestrians, most likely you will face the same challenge. Probably you will also need to go through the same path like we do. So again, this is from the without our local agency support, we cannot go that far. We probably just stop somewhere very close. It's supposed to be future work, but since the project has been finished 1 year ago, so future work has become a current work. After the project finished, in fact, our collaborators, another collaborator think this idea could be very interesting for other states. So we reach out, other than the city of Arlington, around the university campus. They also reach out the Utah Department of Transportation. They also like the whole system. They also provide fundings for us to evaluate our solutions. And in the meanwhile, they provide resources, we build more function into it. So now we are working on a few things. Hopefully in the future, we can also provide additional webinar to introduce the research fundings and see if it can be used by agencies or our companies. The first is near miss is we are using LiDAR to capture near misses. So it's trying to capture a different type of near miss. In fact, that's a lot of near miss every day. And also, we are also exploring some very bold operations, how to collaborate together with the controller and the cabinet. So we have a dynamic flashing yellow arrow. Right now, dynamic flashing yellow arrow is like a program by controller, but I think based on the pedestrian tracking, we can have a more dynamic flashing yellow arrow or dynamic all red without flashing the cabinet. It's a working process. Hopefully in the future, we can present these efforts. And also, we also explore other options, like a couple LiDAR with other physical systems. Like we already finished in-house, in lab, coupling LiDAR sensors with street light system using some power relay. And also we kind of coupled with our LiDAR perceptions with connected vehicle infrastructure. So LiDAR sensors can be used to generate emulated BSU, PSU, and broadcast to real connected vehicles. They make some pedestrian awareness. That's also a good way to improve the safety. This hopefully we can have a chance to introduce in the future. So this pretty much we have for this project, and a little bit of introduction for future. So first, this project, this is our first LiDAR project. It was funded by National Institute for Transportation Community at Portland State University. It is a national UTC. We also thank City of Arlington, Irvine, Texas for their support for LiDAR sensors and provide a network. I didn't list Utah DOT here because this effort is still before we contact Utah, but in the future, you're gonna see we also acknowledge Utah's help as well. So if you have more information or questions, please feel free to contact me or another speaker, Sirisha. Thank you very much. Now I think we have some time for questions.
Hey, thanks, Taylor. Great presentation. I see there are a few questions and comments. I will start at the top. How important is AI implementation to improve transportation safety, and how?
I would say AI is very important to perception software. In fact, at this time, we haven't really applied a lot of AI for application software, but all the application software I built is based on accurate perception software. So perception software for outdoor application is very complicated. In fact, we have even the perception software I'm using, I found quite a few glitches. I have to use a workaround to avoid those errors. But I'm hearing that some companies has been using some deep learning AI to significantly increase the accuracy of performance of perception software. So I'm looking forward to others presentation in the future about the system as well. Yeah.
Next up is a comment from Mark Taylor. It says, I love what I'm seeing with the future of LiDAR. In regards to Dr. Kothuri's comments with measuring perception reaction time and updating PED data, a growing trend is to provide more and more time to pedestrians. As a result, practitioners are forced to go with longer and longer cycle lengths. It would be interesting to see new research with longer cycle lengths and as a result, increased jaywalking and the problems that this now creates with pedestrian safety. Do you know of any research that looks at that trend or how LiDAR could help with this?
So this question for Sirisha, I think. Pedestrian studies.
Yeah. Yeah, I think, previous research has shown us that we need shorter cycle lengths for pedestrians because the longer the cycle lengths are, it increases delays for pedestrians. But I agree that it'd be interesting to look at a study that explores some of this even more. I think there is interest in using LiDAR as a solution for intersection studies. And so, yeah, I think this is a question to be explored.
Yeah, I think one point I want to make here, in fact, Sirisha found out using different pedestrian push buttons, audible or not, and also they can change the effective perception reaction a lot. In fact, the two intersections we studied, they are so different. One reason, as Sirisha mentioned, is about we have audible, newer push button. The other one is they have a smaller waiting area, because that's kind of island waiting area. So those things could affect our walk time a lot, but haven't been addressed by Greenbrook yet. So hopefully, if this research can continue, we can provide some suggestion to our AASHTO committee to update that part. Yeah.
Next question, if you are integrating trajectory data with SAT, what is the method for detecting pedestrians crossing against the cycle against false positives?
I'm not sure I understand this question, but overall is I'm using the zoom method to instead of using maybe the time steps very high resolution trajectories for two reasons. One reason is if we track a vehicle, let's say 10 times per second, for sure we can get a pedestrian, we can get their trajectories, but the trajectory itself take a lot of computing time and bandwidth to upload. Then we slow down our whole overall performance. The second is sometimes perception software is not 100% accurate. Sometimes in the middle, they may make some errors, and then kind of there's some temporary fluctuation for perception, at least the perception software I use. So I think using from zone to zone is kind of using the average, will be more tolerant to errors. Yeah.
Could you share how you validated pedestrian volumes and PR time accuracy, and what were the accuracy ranges?
Yeah. PR time, in fact, is very accurate because that's what I observed. For the perception volume, I would say it is sometimes is not very accurate, especially the pedestrian volume are very high. It happens at UTA Boulevard intersection because we have such high pedestrian volume and such a small waiting area. So pedestrians just stay too close. Sometimes perception combines them into a bigger person, a small vehicle, things like that. It happens from time to time. So I would say this volume accuracy is beyond my applications. It's gonna be rely on the performance improvement for perception software from LiDAR companies. Once we have that, we should have I would say overall, if we have both perception and application, we should have almost 100% accuracy. I can do a lot for the at my side, but I cannot do anything with the perception. I just wait for their improve. Yeah.
Yeah, and I think I just wanted to add that, you know, that occlusion phenomenon that Taylor's describing is not just limited to the LiDAR. All the other sensors also have that same issue, and it's really difficult to make or track pedestrians when they're walking in a group. So it's something that, you know, we will have to like watch out for as the technology and the algorithms continue to improve.
I think the next question is kind of building on that. They wanted to know what's the PR time difference between audible PED buttons and regular PED buttons. You showed numbers, but they're wondering, is there a percent difference?
I think we did not compute the percent difference because we didn't have both at the same location. So at the location, and as Taylor mentioned, our measure also took into effect the waiting area, and there was differences in the size of the waiting area between both those locations. But we did see that is upwards of 5, closer to 6 seconds in one location, and then the other one was 2 seconds. So that's a considerable difference, and that will affect the total time the pedestrian needs to get across to the other street. So it has implications. So, but yeah, we did not compute the percent difference because we didn't have both at the same location.
A couple questions here about cost. One person wonders, how much does the system cost currently for a single intersection setup? And someone else is just wondering how much does a project like this cost to set up and operate?
I would say LiDAR is still a special equipment. It's still more expensive than the radar or others. But different product, I cannot say the price because I'm using a huge academic discount on that. And also over years, the price changing, sometimes go up, sometimes go down due to the, but overall, I think still for the same function, let's say vehicle detection, those basic functions, I would say its competitiveness is not as much. But if you consider its potential for all the others, like to protect vulnerable users, LiDAR sensor, as I said in the slides, is provide a high ceiling for those applications. So we will not restrained by the physical features of sensors. We can build many more functions using LiDAR than the traditional video or LiDAR sensors. So if you consider the whole overall package as the cost may not be that intimidating.
What does one of the LiDAR systems cost? Oh, you may have already touched on this, including associated software. You may have already answered this kind of because there are different brands.
So the best way is just sending letters to LiDAR companies. So they're gonna give you a call, set a meeting to explain the pricing policy. That's probably the best way because I cannot really speak for them about the price. I don't even want to give a number. That could be misleading.
So a lot of research in pedestrian detection uses infrared. How is this different from LiDAR?
Yeah, so we've tested infrared at intersections, specifically in terms of a thermal camera. One difference is that the infrared can be sensitive to heat because it uses body heat to detect a person. So we have seen lowered accuracy on days, especially when it is too hot, and so there's no difference in temperature between the body heat and the ambient heat. So that's one challenge. Also, infrared cameras are generally being used for trails and sidewalks and other features because they do detect anything based on that heat signature. So you could have a number of false positives with vehicles and others. So I think the LiDAR is definitely more accurate in such situations.
Yeah.
Has there been any consideration to use this technology to adjust pedestrian signal times in real time based on how close they're getting to the end of the crossing?
This is, in fact, is a ongoing process. So we have, as I said in the presentation, we are designing some very bold actions, trying to provide a dynamic flashing yellow arrow to separate the concurrent pedestrian with the permissive left turns. And also, we can even provide some dynamic all-red clearance to if the pedestrians are so slow, we don't want to be trended when the vehicle begin to enter the section. So those things, and we have some in-house testing. We can prove it's doable, but is not ready to share with others yet. Yeah, but it's due on our roadmap.
Thank you. Keeping an eye on time, I'd say we have time for one or two more questions. How did LiDAR perform in different weather conditions?
That's a very good question. In fact, this is a question asked by UDOT, the first question asked during the snow, things like that. So my answer will be, it's a very good, reliable, because we deployed 2 intersections in Texas since 2020. So if you remember, Texas in the last 2 years have experienced the worst winter storm in 2 years in a row. And also, of course, in the summer, we have a frequent thunderstorms and the rain, things like that. So whenever I have such a situation, I simply just do my best to open my computer to watch the performance. And also for Utah, Salt Lake City, I also keep an eye on my app. So to expecting Utah have a heavy snow, so I can watch the LiDAR's performance. In fact, it also performs very well. It's fair to say the performance indeed deteriorate a little bit, but not reach the point or the whole system collapse, not yet. So we can still hold it. We can still see the lane by lane detection. We can see the vehicle moving, but of course we can see more noise there, but it won't affect our basic applications.
Okay, great. Right, well, I just put a link in the chat to the project webpage. If you go there, you can find more information, plus the researchers' contact info for those of you who have questions that didn't get answered today. But I will go ahead and wrap this up. So that concludes our webinar. And thank you for a great presentation, Taylor and Sirisha. And thank you everyone for joining us.
Thank you for having us. Okay.
Thank you.
Bye-bye.